All right, let's dive right in. Today, we're taking one of the most sensitive, most delicate components in all of electronics, and we're going to hack it. We're going to transform it into two of the most essential tools you could ever have in your workshop. So let's get started and see exactly how it's done.
It's a great question, isn't it? Electricity is this powerful, invisible force all around us. And if you want to understand it, if you want to control it, you've got to be able to measure it. You need to measure its pressure, that's the voltage, and its flow, that's the current. And today we're going to build the tools to do exactly that, all starting with just one simple part.
And here it is. Meet our hero component, the galvanometer. Now you should think of this thing as an incredibly sensitive detector. It can spot the absolute faintest whisper of an electric current, just enough to make its little needle twitch. But, that's also its biggest weakness. If you hook this thing up directly to any real power source, poof, you'll instantly fry it. So, how do we protect this delicate heart and actually make it useful?
Okay, mission number one. We're going to turn this super sensitive current detector into a robust voltmeter. The challenge is to take a device that can only handle a tiny fraction of a volt and upgrade it so it can safely measure a much, much higher voltage.
So what's the secret? Well, the trick here is that we're going to put another component in the way to basically act as a bodyguard for our galvanometer. Our goal is to measure up to 10 volts. And the method is surprisingly simple. We just add a special resistor, they call it a multiplier, in series. This means all the electricity has to flow through this new resistor first, before it ever gets to our galvanometer. And of course, there's a little math that makes this all possible. But don't worry, this formula is really elegant. It tells us the exact value of that series resistor RS that we need. It's just the full-scale voltage we're shooting for, divided by the galvanometer's maximum current, and then we just subtract the galvanometer's own internal resistance. So let's plug in some real numbers and see it in action. Okay, so here's what we're working with. Our specific galvanometer has an internal resistance of 50 ohms, and its needle swings all the way to the end of the scale, we call that full-scale deflection, with just one tiny milliamp of current. That's 0.001 amps. And our goal is to make that needle hit that exact same full-scale point, but when we're measuring 10 volts. All right, let's just substitute those values right into our formula. The value for our resistor, RS, is going to be 10 volts divided by 0.001 amps. That part of the equation tells us the total resistance our entire circuit needs to have to limit the current and keep things safe. And that comes out to a nice round 10,000 ohms. Now remember, our meter itself already provides 50 ohms of that resistance, so we just subtract its value from the total we need. And there's our magic number. We need to add a 9,950 ohm resistor in series. This resistor is going to do all the heavy lifting. It's going to drop almost all of the voltage across itself, allowing only that tiny, safe 1 milliamp of current to flow through our sensitive galvanometer. And just like that, mission accomplished. We have a working voltmeter. Now the big takeaway here is that a voltmeter needs to have a really high internal resistance. This is so that when you connect it to a circuit, it only sips a tiny, insignificant amount of current. That way, it doesn't actually disturb the very thing you're trying to measure. All right, one tool down, one to go. Now let's take that very same galvanometer and completely flip the script. We're going to rewire our thinking to tackle a totally different beast, measuring a large flow of current. This time, our goal is to measure a full ampere of current. Now that's 1,000 times more than our little galvanometer can handle on its own. So instead of putting a resistor in the way to block the current, we're going to do the opposite. We're going to create a bypass. We'll add what's called a shunt resistor in parallel, which basically gives the vast majority of the current an easy path to flow around our delicate meter. And, naturally, a completely different setup requires a completely different formula. To find the value of our shunt resistor, RSH, we multiply the galvanometer's maximum current by its resistance, and then we divide all that by the total current we want to measure, minus that tiny little bit that's still going through the meter. So let's look at the numbers for this new mission. It's the same meter as before, right? 50 ohms, 1 milliamp full scale. But this time, our target is a whole ampere. What this means is that when 1 amp flows into our new ammeter, we want exactly 0.001 amps to go through the meter, and the rest has to take that bypass. Okay, time to plug those numbers in. So the top of our fraction, the numerator, is the meter's current times its resistance. And the bottom, the denominator, is that total current we want to measure minus that tiny fraction that's going through the meter itself.
This simplifies down to 0.05 divided by 0.999. Now you can already see what's happening here. Almost the entire amp of current, 0.999 amps to be exact, is being diverted through this new shunt path. So what kind of resistance does that path need?
The answer is tiny, incredibly small, just about 0.05 ohms. This is a very, very low resistance path. It's basically an electrical superhighway that encourages almost all the current to just bypass the galvanometer completely.
And there you have it, an ammeter. Now the core principle here is the exact opposite of the voltmeter. An ammeter has to have a very, very low resistance. That way, when you place it into a circuit to measure the current, it doesn't add any significant new obstacle to the flow. It just lets the current pass right through.
So we just used the same galvanometer and a single resistor to build two totally different tools. How is that even possible? Well, the secret, of course, is all in the wiring. Let's put them side by side and really break it down.
This right here, this is the whole shebang. For the voltmeter, we add a high-value resistor in series. This creates a high-resistance tool that you connect across 2 points to measure the pressure difference between them. For the ammeter, we do the opposite. We add a low-value resistor in parallel. This creates a low-resistance tool that you have to insert into a circuit so you can measure the flow through it. See the difference? Series versus parallel. High resistance versus low.
Feeling inspired to build your own? Excellent. Before you go grabbing your soldering iron, let's just quickly run through a few crucial pro tips from the source material to make sure your project is a total success.
Okay, first and most important, you absolutely have to know the specs of your specific galvanometer. Precision is key, so try to use 1% tolerance resistors if you can find them. Oh, and this is a big one. Always check the power rating of your components. That little shunt resistor in the ammeter can get pretty hot. If you want to measure multiple ranges of voltage or current, a selector switch is going to be your best friend. And finally, especially for those ammeter shunts, try to use parts that don't change their resistance when they heat up, because that could really throw off your readings.
So when you boil it all down, it's pretty amazing. With a little bit of math and one extra component, a super delicate detector can be transformed into two incredibly powerful measurement tools. It really makes you wonder, doesn't it? What other powerful capabilities are just waiting to be unlocked?